Alright, welcome to lesson 4. So we just learned about how to differentiate exponential functions, and in particular talked about the exponential function with a base of e, or e to the x, and learned something pretty cool about that function. And so now we're going to take a look at its inverse function, which is the natural logarithm, or ln of x. And so we're going to go ahead and find the derivative of that function, and also take a look at and find the derivative of any log function. In much the same way that we did with e to the x, it's helpful to sketch a graph of the function that we're going to find the derivative of, so that we can conceptualize what should the derivative be about. Like, what is it going to be approximately, at least in terms of how the function will behave. We can maybe even sketch a very rough sketch of the derivative, and so that way when we go to find the derivative, we know about what we're looking for. We can kind of tell if we're on the right track or not, and we'll be better prepared to actually prove what the derivative is. Once you've done that, write down as many properties of logarithms as you can recall. We went over a bunch in the Summer Academy notes. If you can't find those, you can go back and rewatch that particular video. Trust me, they'll be very helpful, not just for proving the derivative of logarithms, but also just in general in dealing with any type of logarithmic or exponential function. Having those properties at your beck and call will be very helpful. Alright, so here's the graph of natural log of x. I've also graphed e to the x, because the inverse of e to the x is natural log of x. Notice it's been reflected over the line y equals x. If you've forgotten about inverses, definitely go take a look back at your notes, or watch that piece of the Summer Academy videos again, because we'll talk about inverses a lot throughout this course. And looking at this function, natural log of x, we should be able to ascertain some key characteristics that its derivative should have, just like we did with e to the x. So what do we notice about the slope of natural log of x? Well, let's start at the furthest left we can. Well, notice natural log of x doesn't start being defined until x is greater than 0, which means that when x is 0, our derivative won't have a derivative, right? There will be no derivative at x equals 0, because it's approaching, it's not ever actually going to get to 0. Okay, well, so that's a big hint first off, right? Our derivative won't be defined when x is equal to 0. Now let's think about what the derivative should be as we get right past 0, or very, very small values of x. Well, it's going to be very, very steep and positive, meaning it's going to be, as we get smaller and smaller values of x, the derivative should be getting closer and closer to positive infinity, right? Very, very steep. Another big hint. Okay, so the derivative is going to be very, very steep and positive here, and as x gets bigger, the steepness of our function natural log, or the slope of the natural log, is beginning to get shallower and shallower, meaning the slope, while remaining positive always, will get smaller and smaller. Okay, so think to yourself, what is a function, just the simplest function you can think of, where if we plug in 0, it's going to be undefined, but if we plug in the value right to the right of 0, just to the right of 0, we're going to get a huge positive number. In fact, that the limit of that function as we approach 0 from the right is going to be positive infinity, right? Because the slope of the function natural log of x is approaching positive infinity. Also, this function should have the characteristic that as the x values increase, the slope, as we can see, is decreasing. So the derivative should have the property that as the x values increase, the derivative is going to get smaller and smaller but remain positive. Well, this is a pretty big hint, so take a second, pause, and think about it. Hopefully, in considering all of those different characteristics, you realize that this would work, this would mimic the function 1 over x. Because if you think about 1 over x, when x is 0, it's undefined. When x is a very, very small positive value, this is a very, very big positive value. And as x increases, this is going to get smaller and smaller, but always remain positive. So in the back of our minds, we should be expecting to get a derivative function of something like 1 over x. Even if it's not 1 over x, at least it should behave similarly. And we might just get lucky enough and find that it is, in fact, 1 over x. Okay, so now what are some properties of logarithms that you can recall? And there are a few that are going to come in handy. So if you haven't already, write a couple down, and we'll take a look at the list of some that come to mind for me. So here are just a couple of identities and properties for logarithms that are used pretty often, that are really helpful to just have memorized so that whenever you need to pull them out, you can. The first is that if you have, and I used u and v here, so if these are just functions or expressions or whatever they are, usually we'll think of them as functions in terms of x, but the idea is pretty clear here. Ln of u plus ln of v is just the natural log of u times v. Natural log of u minus natural log of v is just the natural log of u divided by v, and vice versa, obviously. Natural log of u to the a is a times natural log of u. That's very helpful. And then this is called the change of base property that we talked about briefly over the summer, and this is very helpful as well. So if you have log base a of b, you can rewrite it in terms of the natural log. I talked about how incredibly helpful this is. This way you never ever have to actually compute log a of b. You just have to be able to compute the natural log of something, and that's incredibly helpful, particularly when it comes to finding the derivative. So log base a of b is natural log of b divided by natural log of a. So keep these in mind. We will utilize them as we go through and prove a couple of different derivatives. So now let's go ahead and actually try and figure out what the derivative of natural log of x is, as in the back of our mind we're hoping that it ends up being 1 over x, as it seems like that function would work pretty well, but even if it's not, hopefully it'll look something similar, and that will help us move through our proof. Alright, so here we're going to prove the derivative of the natural log of x. And when I say prove, there might be a couple things that we go through, that we talk about, that I say you kind of have to take my word for it, but they should be pretty self-intuitive, and we just don't want to spend the time right now proving them, but you certainly could go back and figure that out on your own. So whenever I want to prove something, I got to start with what it is that I have to begin my if-then statement with. So what I want to be able to say is, if this is my function, and it's ln of x, then the derivative will be this. So I'm going to start by saying, here's my function, let f of x equal ln of x, and now I'm going to find the derivative. So as usual, I'm going to use the definition of the derivative, right? We know how to find the derivative of something. We take the limit as h approaches 0 of f of x plus h minus f of x over h, and hopefully we can work that out and actually evaluate that limit so we can figure out what the derivative is. Here's the statement of the derivative, and what we'd like to do is think about a general plan, and then I'm going to kind of move a couple steps ahead at a time. I want to get this done in an orderly fashion, but also efficiently. If we try and evaluate this limit currently, and I insert 0 for h, you'll notice that I'll get 0 divided by 0. And so what we need to do is try and manipulate algebraically so that we are able to evaluate our limit by plugging in 0 for h. There are a couple things that I want to take note of. The first is that I have this natural log statement up here, and so I need to manipulate it. So I want to try and utilize some of my natural log properties. And further, I also don't want to have two natural log statements. That's kind of a pain. So if I could somehow condense this into one natural log statement, that would be pretty helpful. I also don't want you to think that this is a method that can be just thought of on the spot. This is something that people worked on and came up with. And we're going through it today in 5 minutes, but you shouldn't think yourself as inferior to anyone else simply because it's not intuitive to you in the instant. It would require a lot of hard work and a lot of time. So our goals for this are, first off, to get this in terms of one natural log statement, and then once we have it in terms of one natural log statement, to kind of look at it and say, okay, how can I manipulate this so that I can actually take the derivative? So let's utilize our natural log properties. That we have natural log of something minus natural log of something else, natural log of that something divided by that something else. And then also that if we're dividing by h, we're multiplying by 1 over h. Okay, now notice that I have something, this is 1 over h, multiplied by the natural log of x plus h over x. Well, that means that I can take this coefficient and I can move it to the exponent inside my natural log. At the same time, I can also notice that x plus h over x can be simplified a little bit because that's x over x plus h over x, and x over x is going to be 1. Okay, so notice here I now have one natural log statement, and inside my natural log statement I have 1 plus h over x raised to the 1 over h. And at this point, I want to start thinking about how I'm going to eventually evaluate my limit. And the reason that we can kind of think about this currently is that we just recently saw a limit that looked very similar to this. And the similarity came in that we took the limit as n or x approached infinity of 1 plus 1 over that value raised to that value. So that was actually how we computed Euler's number, right? E is equal to the limit as x approaches infinity of 1 plus 1 over x raised to the x power. Go back and you can quickly take a look. We took that down in the last video. So if we can start manipulating this limit statement so that we end up with something that looks like 1 plus 1 over x to the x as x approaches infinity, then we can evaluate that limit. And so that's kind of in the back of our mind as we try and move forward here. And if we can make that happen, we're going to be in good shape. Notice that we're getting close. The problem is that we have this x over h over x and 1 over h in the exponent, and it's h approaching 0. So what I'm going to have to do is what's called a substitution. I'm going to have to create a new variable that will represent these variables here. And so that way I can make this work a little bit easier. And the way that I'm going to do that is I'm going to create a new variable, call it u, and I'm going to say that u will represent h over x. And I got to keep this in mind because when I'm all done with my limit, I have to go back, and wherever I see a u, I have to put an h over x. But in the meantime, anywhere that I see an h over x, I can write u. So I'm going to have u right here. And then what will 1 over h be? Well, if I solve for 1 over h, multiply by x on both sides, and then I'll have ux equals h. So ux equals h. That means if I invert both sides, that 1 over u times x equals 1 over h. Okay? Now the last thing to consider is what will happen to u, since this is my new variable, as h approaches 0, because that's what the limit will be looking at. Well, as h approaches 0, u is equal to h over x. And as h approaches 0, this goes to 0, and so u will also go to 0. So the limit stays as h approaches 0. All right. So I now have the limit as u approaches 0 of ln of 1 plus h over x is now u raised to the 1 over h, which is 1 over u times x. So now I have the limit as u approaches 0, and my expression is almost entirely in terms of u. And if it's entirely in terms of u, and I can get it to be 1, for example, and I can pull the x out, then I would just have whatever this expression of x is on the outside times 1. Okay, well that would be nice. So let's try and get this x out of here. Well, 1 over ux is the same as 1 over u times 1 over x. And if I have an exponent with one thing times something else, I can take one of those exponents and move it outside. So that's what I'm going to do. All right, so notice that I had 1 over u times 1 over x, and now I've split them up. So it's the natural log of 1 plus u to the 1 over u, all to the 1 over x. Well, if I have natural log of something, let's consider this something, this green part, raised to the power of 1 over x, I can take that exponent and write it as the coefficient. So that's what I've done there. And now, notice this. If we are taking the limit, and within our limit we have some constant term, meaning something that isn't in any way dependent on u, or whatever the limit, the variable of the limit is, we can pull that out because it won't be changed by the approaching of u to the value 0. This is independent of that. So I can actually factor this 1 over x out so that now I'll have the limit as u approaches 0 of something which only depends on u. Alright, I factored out the 1 over x, and now I am very, very close, and hopefully you can see how. Because remember that when we started off and we looked at, I think it was at this point over here, we said this looks eerily similar to the limit that I used to actually compute e. And this is looking even more similar. What we need is the limit to approach infinity, and then we need this to be 1 plus 1 over whatever that variable is, raised to that variable. So notice that we're just one substitution away. Because if we create a new variable, which is related to u in a certain way, then the limit will all of a sudden go towards infinity. It will be 1 plus 1 over that new variable, raised to that new variable. And so the substitution we want to make is we want to say, let's make this new variable, let's call it n, and let's have n be equal to 1 over u, which means that u is equal to 1 over n. And if we make this substitution now, wherever we have a u, we'll put a 1 over n. Wherever we have a 1 over u, we'll put an n. So this will now be 1 plus 1 over n to the n. Okay, what about our limit? As u is getting closer to 0, what is n getting closer to? Well, n is equal to 1 over u. As the denominator gets smaller and smaller, this whole thing gets bigger and bigger. So n will be approaching infinity. So now my limit will be as n approaches infinity of natural log of 1 plus 1 over n to the n. And that is going to look very, very similar to something that we can actually evaluate. Alright, so at this point, we would know how to take this limit if it weren't for this natural log here, because the limit as n approaches infinity of 1 plus 1 over n to the n is the value e. The only issue is that we have this natural log here. Well, similar to how we can factor out a 1 over x, we can actually change the order. We can take the natural log second and take the limit first. And the reason we can do that is that the natural log is just an operation on some value. In other words, it says, find the exponent that you must raise e to the power of to get whatever this is. And so we can take the natural log after we take the limit. It won't change the ending value. Similar to how if you factor out 2, it won't change the ending value of the limit, whether you multiply by 2 at the beginning or multiply by 2 after you take the limit. So this is the part where I'm not going to prove that to you right now, but we can go ahead and take the natural log out, and you could figure this out on your own. But we're going to take the natural log after we take the limit. And another way to think of why this makes sense is that if n is approaching infinity, what it's actually affecting is only the argument of the limit, of the natural log. And so we'd really be, when we're taking the limit of this, we'd really just be looking at what's occurring in this argument here, and then taking the natural log of it. So it makes sense to actually take the natural log after we take the limit. And at this point, we are in great shape, because we can evaluate this limit. This is the definition of Euler's number. The limit as n approaches infinity of 1 plus 1 over n to the n is 2.718, blah, 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 on forever and ever. It is the value e. And so here we can now evaluate the limit and evaluate our expression. We will have 1 over x times the natural log of e. But wait a second. What's the natural log of e? Remember, the natural log of any value is the exponent that I must raise e to get this value. Well, what do you have to raise e to the power of to get e? 1. So this is just 1 over x. And this means that the derivative of the natural log of x is 1 over x, which is exactly what we hypothesized by looking at the graph of natural log. So a couple questions you might have, and the first is, remember I made these substitutions, u and n, and the way that we were able to make them is that we'd have to come back at the end, and wherever we had an n, we'd have to substitute back in a 1 over u. And wherever we had a u, we'd have to come back and substitute in an h over x. But because when we evaluated our limit, we ended up with no n's and no u's, right? Well, of course we had no u's, but we had no n's, so there was no need for us to go back and substitute back in. And that won't always be the case, but in this case, that happened, and that's great because now we know that the derivative of natural log of x is just 1 over x, which is incredibly simple and incredibly useful because anytime we're working with the natural log function, we can find the slope of this function at any point by using its derivative, which is just 1 over x. So let's go ahead and write down this rule more formally, and then we can go ahead and apply it in some situations. Alright, so the derivative of the natural log of u, and remember we're using u because it won't always be natural log of just x. We might have natural log of 3x plus 5, and that means we have to take the derivative of the outside function and of the inside function, right? It's the chain rule. So if u is a differentiable function of x, then the derivative of natural log of u is 1 over u, just as we saw. ln of x, the derivative is 1 over x. So it's 1 over whatever the argument is, times the derivative of whatever that argument is, or du dx. Let's take a look at a quick example here. The derivative with respect to x of the natural log of x squared plus 1 is going to be equal to 1 over x squared plus 1 times the derivative of the inside, which is 2x plus 0, or 2x, meaning the derivative is equal to 2x over x squared plus 1. All right, there's one more law that we need to learn, and then we'll be able to work on some questions. Okay, we looked at natural log, and now we can take the derivative of natural log for any function, any natural log of anything. But we might have a situation where you have a logarithm with a different base, right? Where you're asking what is the exponent for a different base that would give you this value. And here we can utilize the change of base, which says that if we have log base a of x, so we have some function, log base a of x, maybe it's log base 2 of x instead of log base e of x, then we can rewrite this as the natural log of x divided by the natural log of a. And so if I want to take the derivative of the of log base a of x, what I'm doing is taking the derivative of this over here. So the derivative of this with respect to x is the derivative of this with respect to x. But notice that natural log of a, that's just going to be the value of the base, whatever it is. Here I just used a because it could be anything. But this is not x at all. This doesn't depend on x at all. This will always be the same. So I can factor this out and only take the derivative of natural log of x, which I know how to do pretty easily. So this will be 1 over the natural log of a times the derivative with respect to x of the natural log of x. And so I can easily find the derivative of the natural log of x. That's just going to be 1 over x. And so this will be 1 over natural log of a times 1 over x, which is equal to 1 over x times natural log of a. and that's the derivative of log with a different base of x, log base a of x. And so we can apply this understanding to now if I have log of some different base, and then instead of just having x, I have some function of x, so we'll call it u, and all I'll have to do is multiply by the derivative of whatever this function u is. So let's go ahead and write that down. Okay, so the derivative of log with a different base, so log base a of u, and this is an a, by the way. If u is a differentiable function of x, then the derivative of log base a of u. And so let's follow what we found over here, which is that if we had log base a of x, we ended up with 1 over whatever the argument was, which in this case is u. So it will be 1 over u times the natural log of the base, so times natural log of a. And then all we have to do is, because this is a function of x, so it's not necessarily going to be x, it could be 3x plus 2, we then just have to multiply by the derivative of whatever's inside. In other words, du dx. So let's take a quick example here. Let's look at the derivative with respect to x of log base 2 of x squared. Well, this is going to be 1 over. U in this case is x squared, so it will be x squared times natural log of 2. And of course, a natural log of 2 is just some number, but we will just write it as natural log of 2 because it will be much cleaner if we write it like this. But just know that this is the value that you raise e to the power of to get 2. Okay, so it's just some number. And then I have to multiply by the derivative of the inside, so the derivative of x squared, which is 2x. And so this will just be equal to 2x over x squared times natural log of 2. All right, I'm going to give you a couple to practice on, and we can discuss them in class. Okay, here are 4 for you to complete. Make sure that you are practicing implementing the couple of theorems that we've discussed, and we will present these in class.